Right. Again, this is my video presentation of ChiSquare and Pedigree analysis. I'm going to explain the following ChiSquare analysis from start to finish. You can see that you have a homozygous dominant purple flower and a homozygous recessive white flower crossed to form your F1 generation. After they self-fertilize, you can see a 3-to-1 ratio in your F2 generation of purple to white for a total of 150 progeny. In order to calculate your ChiSquare value, you have to have your total of progeny as well as your expected. In order to find your expected, you have to take your 3-to-1 ratio and multiply it by your total observed progeny to get your expected. Once you have your expected, you can plug it into your ChiSquare, which is the sum of the observed minus the expected squared over the expected, and you do this for both genotype or phenotypes present. Get 0.5 for the purple and 1.5 for the white, giving you a 2.0 ChiSquare value. Then you have to define your degrees of freedom, which is n-1, n being the total number of phenotypes present in the progeny. So n being 2 minus 1 gives you 1 degree of freedom. If you go to your table 3.5, which is in your book, you can see that P falls between 0.1 and 0.5, meaning that there is a high probability that the difference between the expected and the observed values is due to chance. And there's really no significant difference between the expected and the observed values. Number 2, purple kernels are dominant over yellow kernels in corn, and full kernels are dominant over shrunken ones. A purple plant with full kernels is crossed with a yellow plant that has shrunken kernels, and these are your progeny that are obtained. The question is, what are the most likely genotypes of the parents and the progeny, and then you have to do a ChiSquare test. There's a few things required to solve this problem. Those are which alleles are dominant, which are recessive. You have to know the genotypes of the parents so you know which ones to cross and what your outcome will be. You have to know your observed outcome of the progeny, the expected outcome of the progeny, the total number of phenotypes represented in the progeny, and the total number of progeny. And if you look back in your problem, you have all of that, which are dominant, which are recessive, your observed, which you can add up to get your total. And because these numbers are fairly close, you can see that it's supposed to be a 1-to-1-to-1 ratio, which means you can do some testing to figure out which genotypes are the parents. And because you have the total, you can also find your expected value. So there's no information missing from the problem. You have everything you need to solve it. Analyzing the color and shape traits separately, purple is dominant over yellow, full is dominant over shrunken. So you have one heterozygous parent for each trait and one homozygous recessive parent for each trait. And this will give you 1/2 purple, 1/2 yellow, and 1/2 shrunken and 1/2 full. So that means all 4 traits will be represented in the progeny. So now that you know your parents' genotypes, the purple parent with full kernels and the yellow parent with shrunken kernels, you can cross them. And these are your observed values that were given to you in the problem, and your expected value, which would be the total number of these, which would be 400 divided by 4 phenotypes. And since it's supposed to be a 1-to-1-to-1 ratio, it makes sense that it would be 100 to 100 to 100 to 100. So you plug that into your ChiSquare formula, expected minus or observed minus expected squared over your expected, and you do this for each phenotype. These are your results, and then you add all those together in order to get a 2.7. And after that, you have to define your degrees of freedom. The total number of phenotypes, n minus 1, gives you 3 degrees of freedom. go to your chi-square table, find your degrees of freedom, go over, and you can see that our 2.7 chi-square value falls in between these two, which means that there's no significant difference between the expected and the observed values, and that means that the differences are most likely due to chance. Problem number 3. Joanna has short fingers, and this is her family pedigree. This one is Joanna and her husband and their 2 children. This is Joanna's mother and her parents. This is Joanna's father and his parents. And the source of inheritance for this family is most likely autosomal dominant. It's definitely not Y-linked because every male would have it, and it's not X-linked because it's not as prevalent as in females as it should be if it was X-linked. Also, autosomal recessive traits usually skip generations, and you can see that this one is present in every generation. So we can infer that it is a dominant gene. If Joanna and Tom were to have another biological child, the probability, based on the fact that it is autosomal dominant, that their child will have short fingers can be calculated by finding Tom and Joanna's genotypes. Since it's a dominant trait, Tom must be homozygous recessive because he has normal fingers. But because Joanna and Tom both had children who both had normal fingers and short fingers, Joanna would have to be heterozygous, because if she had a homozygous dominant genotype, all of their children would have short fingers. So once you do your Punnett square, you can see that the probability of their next child having short fingers is 50%, or 1/2. Square analysis from start to finish. 0.1 and 0.5, meaning that they're really close. You can 1 ratio, makes sense that it would be 100. Their family pedigree. This one is Joanna. Trait Tom. Square analysis from start to finish. 0.1 and 0.5, meaning that they're really close. You can 1 ratio, makes sense.